Oh, okay, it's ready to go. Yep. Okay, welcome to our weather discussion this week. Very exciting week on so many levels. And I'll apologize right now for focusing on what's gone on in the West Coast and the Pacific Ocean, as opposed to almost equally exciting 1.9 inches of snow yesterday, 0.5 the day before. And in Beaver Dam, they had 6.2 inches of snow. So I have a feeling that lasted and looked like there was, a coating for overnight and so on. Not so for us. And we had the unusual case of snow changing to rain here, which is a New England thing. It's not a Madison thing. And that was interesting. And maybe benevolent, because I was slipping on the way in on the snow on Thursday morning. So I don't mind that happened, I guess. But we got our first measurable snow just about right on schedule. I'll show you this later. I don't have it handy at the moment. But we have, well, I'll save it in fact for that. But we're looking at this beautiful set of images. Pete's truncated all of them on the West Coast starting on Sunday. So we talked about this thing on Friday. Patrick knew about it on Thursday. I hadn't noticed that till Friday morning and got excited about it. Way into the future, this thing was well forecasted. I forget how deep the cyclone got. Does somebody happen to remember that? Was it 942 or something? And it started out well above 1,012, so it was a 70 millibar event in about a day. 60 or more of those millibars of fall were in one day. And I'm sorry I don't have a catalog of all the buoy data that was available during the week. It just, can't do everything. But there were a couple of buoy reports where they were just staggering pressure falls. Partly it's translation, partly it's the development of the cyclone. That's the thing about a stationary observation. You can't separate the two. It's nice to have instead the sort of semi-Lagrangian look at the cyclone moving through space and seeing its sea level pressure keep on dropping. But even in that much more conservative perspective, 60 plus millibars in 24 hours. I mean, it just blows things out of the water. I mean, it's absolutely incredible what happened. So, we're not going to explain it all today. My group is now challenged, all of us together, to try and figure this out over the next several months in our spare time, in our collaborative spare time, because it's going to be a fun project. But we can say a few things about what happened. Number one, look at how this thing just had the, I'll start to give it human attributes. It had the wisdom to stay away from the jagged British Columbian coast. If that had been the case, we wouldn't have a continued persistence of this vortex today. Watch this. So this is all Tuesday, incredible rapid deepening. That's storm number one, and it is an intense little disturbance. Here comes a cloud head that develops into storm number two. That is still our current one, and that's today, right now, 12Z, 15Z on the 22nd. So there's still a discernible disturbance in the Pacific Ocean that originated on Monday, and so it's still hanging around, and it's still feeling intense. So I would imagine, I don't know if I've seen any direct reports of this, but with the pressure falling as rapidly as it did, wind speeds in the Strait of Juan de Fuca, and then also the one that borders the British Columbia coast with Vancouver Island, wind speeds in here near Nanaimo Bay were 100 miles per hour during the day on Tuesday. And that's with the cyclone and a mountainous island in between that. And we had, 500,000 people are without power in western Washington because of the flow through the Cascade gaps with the low pressure offshore and, of course, considerably higher pressure inland. Places like Enumclaw, Washington, had winds over 90 miles per hour, Issaquah, places like that. So, brutal event, even if it wasn't a direct hit in many of these locations. I would love to have been on the southern tip of the used to be named Queen Charlotte Islands. They have a much more beautiful native name. I can't remember it now off the top of my head. They've been renamed. But that would be a great place to have watched this thing roll in. You can't do everything, unfortunately. Okay, where did it come from? And have we ever seen anything like this before? Well, several of us have. What a remarkably similar event to the November of 2019 event that Patrick's doing his work on right now. Not in every facet, but in quite a number of them. So I want to show you some of those. I think first through Viz 5D. Well, before we do that, Pete, let's get a sense of the current observations, both over the continent and over the Pacific Ocean. We'll do that, and then we'll go to Viz 5D. Thanks. So here's let's go to 500 first. I think you might even have that up. Here's the 500 millibar map from this morning. It's slightly less wavy in this portion of the hemisphere than it was on Wednesday and Thursday. I've never seen a wavier flow. It almost looks like Dr. Seuss decided to draw a weather map and just create, ridiculous versions of things that maybe are slightly plausible. And so we have this deep cutoff over the northeastern United States. That has taken its sweet time to migrate to the east. Of course it would. It's divorced now from the baroclinic westerlies. It's cut itself off. That's the nature of these things. It's temperatures in the minus 32 in northern Virginia at 500 millibars this morning, minus 30 at Raleigh. I had a report from Philly that it was mixed snow and rain for a while this morning there. So that's pretty interesting. And I told my daughter that was coming. She didn't believe me. I'm used to that. Here's a deep cutoff that's kind of the whole complex that's controlled the main event from Tuesday and Wednesday, and now the secondary event that's now off the Oregon-Washington coast. Look at how cold it is, minus 34. And that is just, let's see, we're about 5.3 or so kilometers above the ground. The ocean surface temperature is around 10 degrees C, so you've got about a 44-degree temperature difference over 5 kilometers, which means the lapse rate's 8 degrees, which is moist unstable. You know, if you're greater than 6, you have moisture in the air, and it's condensing, you're going to be unstable, absolutely unstable. And we've seen, even, I didn't draw too much attention to it, but the open cellular convection is widespread underneath the cold dome. And in fact, storm number 2 was an amalgamation of such convective activity. If you go all the way back to Tuesday afternoon, Wednesday, watch that thing start to evolve. That's the cold pool aloft, and it's creating a collection of thunderstorms that kind of aggregate for reasons I don't particularly understand, but a lot of tropical dynamicists do. It's roughly the same dynamics. And then when they aggregate, they can really drop the heights and get a sea level pressure feature going. So, and then upstream of that, another just about cut off ridge over the Aleutian chain. So there's wave number 1, 2, flat ridge, 3. There's a big ridge over northeastern Canada, at the mouth of the Labrador Sea, a deep trough over the Greenland Sea. So wildly wavy flow right now. So, and many of them of fairly high amplitude. So it's not surprising it's been an exciting week. I will say, unfortunately, had there been nothing off the West Coast, this would be the topic of interest all day today. But we just can't do it. We can't do both. So that's a really interesting event. And exceptionally cold air for this early in the year. Well below minus 30 over Virginia and the Carolinas to Piedmont. That's not normal. Okay, that's really unusual and exciting. And you have to go all the way to the archipelago to find minus 30 again in the same longitude swath. So that's very isolated cold air. Same is true here. You can't find minus 34 anywhere in the state of Alaska. Even at Nome, it's minus 32. Wild. Okay, really wild. Okay, let's take a look at 850 if we could, Pete. And then we'll look at a jet after that. So here's 850, same features show up. Here's the deep low that's kind of sitting right over Albany, almost over Albany, maybe over, I don't know, White Plains or something. Pretty intense cyclone, and it's windy. Some of the drought's been broken in Massachusetts. They had rain yesterday. They may have snow today or tomorrow, a little bit on top of that. And it's pretty chilly in the middle Atlantic states, and very windy, so that wind is not going to abate. Here's storm number 2 that's getting itself at 850 to look really intense. I mean, when you have an 1197 millibar geopotential height minimum at 850, on any other day you think that's the story of the day. But this is actually like a secondary story after everything that we've had this week. There's the primary cyclone. I won't have time to show you this, but I encourage you to look at the data yourself, especially in the old GEMPAC files that Pete keeps for us. This thing was warm core from the day it started to develop, well, midday on Tuesday. Once it started to really put itself together as a cyclone, it was a perceptible warm core in the middle of that thing. When it finally cut off from this baroclinic zone, it kept that warm core signature, and even on this analysis you can see that. So that doesn't mean it's tropical, but it does mean something about really intense developments overlap between the tropics and the extratropics. I have absolutely no sense as I'm talking to you about the influence of diabatic heating on this development. None. And I'd like to know what that is. So maybe someday we'll figure that out. So anyway, full of interest. And we have a strong northerly flow over us, which will keep us chilly, but there's no real reservoir of cold air to drag further south. So what we have now is what we'll continue to have for some period of time into the future, it looks like. Let's do one last thing, Pete. Look at the jet features at 300. We might be compelled to go to 200 in a minute, but let's start at 300. So here's 300 millibars. Our cutoff feature over the eastern United States has a really significant jet feature off of, on its southern periphery, 130 knots off the Atlantic coast. Then we have this kind of flat ridge, and it's even flatter at 300 millibars as there's a bit of a trough right along the border of Montana and the Dakotas with Canada that has a jet in it. And then here's our deep upper trough off the Pacific Northwest with 150 knots, maybe 160 on the southern western periphery. And then this one I don't like at all. I mean, even I like the winter, as you know, but I don't like to see 110 or 100 knot jet coming straight north on the border of the Yukon and Alaska. That kind of suggests that we're going to get cold in the western part of North America. And once that happens, we can easily get cold in the central part of North America. So lots to look at. But look at how wavy, even at the jet level, the flow really is. And I don't measure this regionally. It wouldn't be hard to do. I just haven't sat down to do it. But I have a guess that, Steve Maverson and I did some work some years ago on another way of measuring the jet. And he found, a day in the 70-year NCEP time series that was the waviest winter day. I think this beats it, just by eye. I think it does. So it'd be really fun to calculate that. I don't know. Let's go to 200 millibars, Pete, because there's no particular evidence of a subtropical jet at 300. There is at 200. So right here off the Southern California coast, across northern Mexico, and then kind of a conjoined jet. I mean, it looks like there's a maximum here and there's a maximum here, right? This one is the subtropical jet. That's the top level of the polar jet we saw associated with that cutoff. So they're close to each other, but they're not sitting on top of each other on the east coast. But this one is entirely separate from the polar jet that brings the cutoff off the west coast. And then you go this far up in the atmosphere in the high latitudes, you don't see anything except the top level of the polar jet. It's 90 knots. It's nothing to sneeze at, but it's nothing like what we saw at 300 millibars. So you're just weaker and weaker. Absolutely no intrusion of the tropics to those latitudes at this time of year. That's the only thing about this whole map that's normal. Okay, let's take a look at Viz 5B. This will be fun. And Patrick, I stole a lot of your time last week. I'm going to try not to do that this week. Here's the sea level pressure at 6C on Monday. And it's from a run that was begun at this time. It was initialized at this time. So I'm showing you every 4 millibars. There's this little cyclone here. Here's Hawaii, just for a little bit of reference. And there's the end of the Aleutian chain. So we're about at the date line, and it's this cyclone here. Let's put theta E on top of that, which I had in a horizontal map. Yeah, so this is equivalent potential temperature at about 1 kilometer, and it's every 3 degrees. A lot of it's ugly, a lot of it because it's over terrain, and then in the tropics it's spotted. This is a GFS forecast converted to Viz 5D, so the GFS has some idea of where convective towers are, at least in its own model world, and so they produce little spots of high theta E. But broadly speaking, in association with this cyclone to the northwest of Hawaii, there's a really broad baroclinic zone. And Patrick, it goes right through the downstream anticyclone. I think we've seen that before. And this is the most intense portion of it. And let's take a look at the two-dimensional frontogenesis, which I also plotted at this time. You got to slide down a little further. Front 2DH. Years ago, Pete, you calculated for me, remember that? And here it is. So there's the cyclone, and this is the warm frontal structure associated with it, and there's a really intense region of frontogenesis. How deep is it? Let's take a vertical cross-section through that. And then we can tilt it up. It's reasonably shallow, right? I mean, this green line is the theta E at 1 kilometer, so it's less than 2 kilometers high, and then it has another counterpart in the lower stratosphere, but that's the lower tropospheric frontogenesis maximum. While we're here, let's take a cross-section of theta E. And so, look at this. Really intense theta E gradient, strongly frontogenetic in the boundary layer, in the lower part of the troposphere, weakly so in the middle troposphere. What does vertical motion look like? I think I'm putting just positive omega on here. I mean positive W, so rising motions are horizontal. And there it is. So it's a weak ascent region, kind of a little stronger in the middle troposphere, and not really very strong in the lower troposphere. That's maybe, it's just maybe a little bit poorly resolved in the model. What I find interesting about this, and I know Andrea's not here, but this is a region of positive horizontal frontogenesis. And theta and theta E are the same this high up in the atmosphere. So this is the warm side, this is the cold side. So I have ascent on the warm side in response to frontogenetic, and subsidence on the cold side in response to horizontal frontogenesis. What's that going to do to these isotropes in the lower stratosphere? You tilt them like that. Watch out, jetogenesis. So you tilt, you're making the tropopause even steeper under the influence of lower stratospheric horizontal frontogenesis. Isn't that cool? It happens every once in a while, and here's a really good example of that. So That is a jet developer, as it turns out. And Andrea did some of her work for a PhD on that. And now she doesn't care about these things anymore. But I still do. So she does a better, more interesting things. Here's the lower tropospheric frontogenesis at 6Z on Monday. So just like Patrick's been saying about his case, this is what's known as a diabatic Rossby wave. There's a little perturbation. Let's go back to the top map, Pete, and we'll look at the theta E, and we can take the frontogenesis off for the time being. We'll come back to it. So this region of frontogenesis that I just took out is forcing ascent, and it's stretching the column, and it's likely contributing cloud and precipitation development, so there's a latent heat component to it as well. That's where the adjective diabatic comes in. And so you have diabatic column stretching, and that spins up vorticity, and that vortex structure just propagates along the pre-existing baroclinic zone. And that's how this thing will divorce itself from the parent cyclone in the long run. And the diabatic heating is likely a major component. We're making a guess about that now because of the similarity that this storm has to the one we've looked at in some detail. We know for sure it happened that way in that storm. And I think this is the same thing here. So let's march ahead a couple of hours and watch what happens in this region. I think it's every 3, so we can go every 6 or so. So look at how strong the baroclinic zone remains, and notice how the isobars in white are being extended out this way. We'll go one more, Pete, to 18Z. And we almost have our own little separate feature there. Let's put the frontogenesis back on, just to see. You know, usually I've been preaching this in 452. Frontogenesis is not a particularly good mechanism for driving cyclogenesis because one imagines vertical motions along a whole lengthy strip. And so how do you concentrate the column stretching and develop a cyclone? But what happens if the frontogenesis is limited in its lateral extent? Like this, it's like a little bullseye. We have rising air on the warm side, sinking on the cold. I don't have any rising air over here because there's no particularly strong frontogenesis. I have no rising air down here. So I do have kind of a localized region of ascent on the ascent side of that frontogenesis maximum. And isn't it interesting that that's exactly where my new sea level pressure is developing? Because all the atmosphere cares about to develop a circulation center is isolated updraft, right? And if this is an isolated forcing mechanism for the updraft, that's going to work, and it does. So let's slide this over, Pete, if we can. This is where you get expert driving from Pete. Oh, it's just perfect. See, Pete said, yeah, I know what you're thinking, and he does. He's actually doing it for me. And then we might as well get the other one on there too. I think it was the frontogenesis. We'll slide that over too. And then we'll look at them, of course, one at a time. So let's, in fact, look at the frontogenesis first and take the other two off. So this is now 6 hours, 12 hours after we first looked. And it's got the same complexion in the lower troposphere. The upper stratospheric part is gone, at least on this cross-section, which is interesting. But that might just be because we moved away from that feature. But we're following this one. And that stays about the same depth and same everything. Let's take a look at theta E on there. Still a very intense horizontal temperature contrast and moisture contrast there. That's interesting. A little bit of that old structure we saw before. And then W. Well, a little bit more intense vertical motions here now. Okay? And not as deeply penetrating. They're only going up to about 5 kilometers, and they're concentrated in the lower troposphere. So this thing is really starting to have an effect on the lower tropospheric column stretching. And as I say, this is a limited region of updraft. We can't see it in this cross-section, but you can imagine laterally into and out of the page, there isn't much dimension to this thing. So this is one little column of ascent, and that spins up a vortex. That's how it does it. Okay? And so let's go back to the top peak.
My wife was watching online and she laughed when you talked about us thinking the same.
Oh, I'm glad she wasn't worried. That would have been worse. Okay, let's go ahead 6 more hours. And in that period of time, suddenly we got a whole new little cyclone here, it looks like. This is 1,016 millibar isobar, so the pressure is below 1,016 in a local spot. Let's put the frontogenesis back on there. Right there, it's limited bullseye. We can slide these over, Pete. Sorry, Tricia. I'm not sure if it's me influencing Pete or the other way around. I'll take the other way. I don't think you want the other way. That looks easy, but it isn't, I can tell you. Let's take a look at the frontogenesis first again. Oh, well. I'd say that's a little bit different, wouldn't you? That's maybe added 50% to the depth. this is getting to be a little bit more robust. It's not changing its lateral extent. I'm gonna guess the vertical motions are a little more intense. I don't remember, actually, let's see. Oh, they're a little bit more intense, but not really in another category. And then let's put theta E in there, and we've got the same basic, really intense lower troposphere temperature contrast, poorly stratified air on the warm side, and then stratosphere is a little bit less steeply sloped along this cross-section. That's of little or no concern for that particular point. So this gets us to 0Z on Tuesday. Now let's go back to the top. And let's get the theta E off. We've kind of traced the diabatic Rossby wave portion of this thing. We don't really have to look at that again. Let's take the mean sea level pressure off too, just to clean it up. Put the pressure on instead. This is at 5.4 kilometers, so it's the approximate 500 millibar level. And here's the 500 millibar isobar itself. I think it's right there. So, really little sharp curvature maxima. There's the shear maxima as well. Let's put the vorticity on there, just in the front of it. QZ. And this is every 4 units times 10 to the minus 5 per second, and we're starting at 12. So remember, our cyclone was right about here, where we're cutting through the maximum in front of Genesis in this location. So just up shear of that is a vorticity maximum of 16, 20, 22.4 times F. Okay, so it's starting to show up as a fairly substantial feature, right embedded, as you might guess, in the trough axis. What about PV at this level? Just see what that looks like. So here's the PV at the same level. And that looks a little bit less impressive. You might say, gee, and it's got a weird orientation. I thought I would see it aligned along the flow, but it's not. It's kind of perpendicular to the flow. For the fun of it, Pete, let's just slide the level of the PV up a little bit higher. If you click on it again, you can get control of that thing. Let's go to a little bit higher level. Oh, well, wait a minute. Now I start to see this thing coming out this way, and this is a much more impressive upper PV feature. The gradient's enormous, and we're only at, what, 7 kilometers, so maybe 400 millibars or 380 millibars. So we don't have to go that much higher to get a peek at really how strong this forcing is in the upper troposphere. So 500 is the level we often look at, but it might be wise to go a little higher sometimes and see. And sure enough, an impressive, extraordinary forcing actually going on here. But let's go back to the traditional view and get the QZ back on, which is the vorticity. Thank you, Pete, for being excellent at driving this. It's a lot to ask. That's one of it, yeah.
Almost actually.
And then, yeah. And then we're at the same level, right? 5.4? Yeah, so there's our vorticity maxima. Let's take the pressure off and put theta on there. And I think it's at the right level. We really should go to 3 kilometers. Let's go to 3 kilometers on that, because that'll be a proxy for the thermal wind. Right there is perfect. This will be a proxy for the thermal wind in this layer from the ground to 500 millibars, and this is the 500 millibar vorticity. And boy, that is a strong horizontal temperature gradient, and it's colder here and warmer here. There's a strong thermal wind coming right across the gradient, nearly perpendicular. Those streamlines of the thermal wind are nearly perpendicular to the vortex structure. There's a lot of PVA by the thermal wind going on here at 0Z Tuesday, and that's right over the cyclone center. So we not only have this diabatic Rossby wave propagation of the little disturbance, but it's now being supported by stuff at upper levels. This has come along, it's a Johnny come lately, but here it comes, okay? And let's take a look now, let's go forward to 6Z on Tuesday. And just a quick peek, mean sea level pressure to see where we are. There's our new cyclone center, so right there, we can take that off and I'll just leave the pointer there. So here's our vorticity maxima, and here is our thermal wind, and there's a decent amount of PVA by the thermal wind just north and northeast of that cyclone center. Let's go 6 more hours. Wow, this vortex structure is getting wild. Look at this. This is much more intense than it used to be. Let's see where the sea level pressure is at 12Z. That's pressure, I think. There's our cyclone center, so let's take it off again. Again, really strong thermal wind, extraordinary advection right in this region. One more time, and then we'll go to some other stuff to show you. 18Z, look at this. You can't even count the intensity of the vorticity. It's something like 6 times F right in there. And then you're seeing the thermal wind cutting right across it in the same location. Sea level pressure minimum will be right here, I bet. Yeah, right in that same location. So there's extraordinary intensification that goes on between 12 and 18Z. 18Z is the time of maximum intensification of this thing. One last thing with Viz 5D I'd like to do is, let's take a look at where does this let's go back to 12Z, I think would be the time we want to do it. Yeah, let's take a look at the PV cross-section. Yeah, I'm cutting right through the strong horizontal temperature. Maybe we can take these off, these other cross-sections for now. And W goes off. And so I'm cutting right through, if we take the vorticity off and the sea level pressure, we'll see what I'm talking about. I'm cutting right through the strong temperature contrast perpendicular to the isotropes at about 700 millibars. And then the vorticity, I also want to be as perpendicular to that as I can be, right into the strong gradient. That's perfect. So now let's see what PV looks like at this time. So here's our PV pendant, steep tropopause. I was interested in finding out where the air at about 500 millibars at this time came from. So I ran a trajectory set. It's right here, it's trajectory 3. Number 3, I think. And so if you slide around, get out of trajectory mode, it'll screw you up. If you slide around, you'll see that I've got the air coming right to that spot, okay, in that cross section. And look what it's doing. It's subsiding into that region. So what you can do now is you can go back in time and find out where's it subsiding from. So let's go back like 6 hours or 12 hours. Let's go all the way back. Right there, perfect. Let's raise theta to the level of where the trajectory cluster is. Maybe a little lower. And then let's put the pressure on top of that as well at the same height. Just so we can assess the geostrophic temperature reduction in that region. We'll slide that up there. And then let's go to the top and take a view of this. So here's where the air is coming from at that time. And look at what we've got. These are the isotropes in purple. There's cold air advection and cyclonic shear. Really intense horizontal winds here, weaker ones here. Exactly what you might expect. Strong cold air advection and cyclonic shear. Let's go ahead 6 hours. And we can't just imagine the air is at the same level. Let's make sure it is. Let's do a south view of this. Oh, nope, it subsided. We got to drag everything down because I want to keep an eye on what's happening at the spot where this air is being forced. Let's take a look now at the top. Whoa, and zoom in. That's even stronger cold air advection and cyclonic shear. And so we're doing exactly what you would expect. We're making this air subsiding in exactly the right environment to make that happen, okay? And let's go a couple more times forward to 12Z will be probably good enough. And even more subsidence. So let's make sure that we're still being forced to subside. Yeah, let's take a look at that. Thank you, Pete. And then zoom in. I didn't think it could get stronger, but it has. This is extraordinary cold advection, extraordinary horizontal shear given by the pressure difference there. You can see the geopotential height lines would be stronger here. So this is exactly how this air at 500 millibars that makes up the upper vortex structure for the subsequent intense development came about. How did it get there? It came from the stratosphere. And it came in northerly flow off of the Aleutian chain. Somewhat hidden and stealthily for a while, but it can't be stealthy forever. And so it comes down as this fist of God, high PV. And downstream of that is where you get your cyclogenesis. Exactly what we were talking about. Okay, so there's more we could talk about there. I want to show you a couple of things on my own PC, and then I'm done. And I guess I was not as fair as I hoped to be. So what about the vertical motion? 700 millibar vertical motion at 12Z, so 6 hours before the intense development. The dashed white lines are the thickness from 1,000 to 600 millibars. And big region of ascent, 12 decipascals per second. And that's what it looks like at 12Z. We'll go ahead, Pete, to the next one. This is the same variable, but at 18Z. I'm sorry, it's such a terrible picture. It doesn't look that good.
Would it be better in the slideshow?
Maybe. You just have to click down there. That's a little better. This is 29 centimeters per second, effectively, for the QG vertical motion. I can tell you, at the same time, in that Viz5D file I was just looking at, the GFS forecast model in the maximum region, which is in the same spot as this, had 91 centimeters per second for an updraft. 91, just shy of a meter per second synoptic scale updraft on a 1 by 1 degree numerical weather prediction model. These are sort of weak thunderstorm updrafts occurring on a synoptic scale. It's no wonder this thing went to town. But there's the big coupling. How do you split it up? So that's the total. Let's see what the next one is. The next one is just the PVA by the thermal wind. It gives you, so not quite in the same area. If we could go back one click, Pete. and the maximum's there, and then the PVA by the thermal wind curls around a little bit more to the west, if we go there, see that? And this is the NBA by the thermal wind. So this is all thermal wind and vorticity advection. Let's split that up. Here's just the shear vorticity advection by the thermal wind, right where the cyclone center is, but not that intense in this storm. How about the other one, curvature vorticity advection? A little bit more widespread, and the couplet for subsidence is even stronger in that. And then I think I have maybe one or two more. This is the across isentrope convergence to the Q vector, so the frontogenetic part of the vertical motion forcing, and it's pretty intense along the cold front, and the warm front kind of gets involved actually in the cyclogenesis as well at this time. That should say 1800. And then here's the subsidence on the cold side, subsidence on the cold side, subsidence on the cold side. And then one more thing. This is the deformation terms that you often neglect. Wow, you better not neglect them. If you want to know why the air is rising in that thermal ridge, this is a big part of the answer right there. And then there's compensating subsidence because we've assumed some things about the simplicity of the flow that are not accurate and in the region of strongest ascent from PVA by the thermal wind. But it doesn't cut it down very much in this storm, just 4 out of 30 or so units, so not a big difference. And I don't know if I have another one, that might be it. That is it. Okay, so as you can see, there's a lot more you can think about with this storm, but I don't want to spend any more of your time. Are there any questions though or comments? Eleanor?
This is probably more a topic question, but what were like the main differences so far that you've seen between this event and like the
Yeah, I can give a comment on mine. I don't have enough knowledge about this one to make any more than guesses. I want to see what the diabatic contribution is. That would be my main thing before I could answer that question. So, and then you can say, okay.
Kind of playing off that, was there the blocking event with the 2019 one?
Not upstream, I
Not
don't think.
upstream?
Yeah, I don't think so.
But not as intense as this one.
Nice.
Yeah.
Is the background still as wavy as it is like today or right now?
I don't recall. I mean, you know, my eye was drawn, because I live on the continental United States, to both the continent and the adjacent waters. In that storm, there was a big anticyclonic wave break over Alaska. But that might have been the only thing that relates to a high amplitude wave phenomena. And I just don't have the more comprehensive view of that storm. So that's a good question. I don't know.
At a basic, just mass conservation level, the air's got to go somewhere.
Yeah, it's got to be made easy to go somewhere. That's the key thing.
Yeah.
It's got to be easy to get it
I
out.
was looking at the kind of ridge building stuff way upstream in the West Pacific that would have helped support this.
Yeah.
But I didn't do any sort of rigorous stuff, but that suggests some sort of link there for me.
Yeah, it's possible. I mean, in the case that we're working on now, in fact, the component of that case we're working on now has to do with where does this upper front come from that comes along and drives the cyclogenesis. And I think it's a combination of a residual baroclinic zone from an upstream cyclogenesis, which was really intense, and then just the general increasingly subsident flow that you get from ridge crest to trough axis. And that reoriented the isentropes into an alignment that allowed the upper frontogenesis process to really go fast and drive the whole thing. And then, of course, it's running into a barely alive diabatic Rossby wave is purely circumstantial, quite the way it is here. So they don't know we don't think they know each other exists. But if they do, that would be really cool. But my suspicion is they don't. So, anything else? Nikhil.
Yeah, so thermal indirect circulation that's generated as like the upper front develops, does that play like a major role in intensifying the system at all, or is it mostly just the vorticity action?
The circulation that develops the upper vorticity availability does not contribute much to the cyclogenesis. I think because it's not even necessarily thermally indirect. I think this is a residual of the old way of thinking about upper fronts. In the sense that it's the transverse motions that really drive the subsidence of the tropopause. I think in this case, when you think about shear vorticity advection, it's going to be a component of vorticity advection, so it has to have an along isentrope Q vector distribution, which means the vertical motions are not partitioned across the thermal shear, they're along it. And so it's not thermally direct or indirect. But it does produce the upper vortex structure, and you also create the strong baroclinicity at the same time. The combination leads to strong PVA by the thermal wind to develop your cycle.
Okay.
So that's how it seems to play out to me.
So that circular, I guess when the upper front came down, it wasn't necessarily from a thermal indirect circulation, it's just.
Yeah, that's right.
chemical
That's what I think. Yes, that's the new thinking, I think, that comes from the vorticity analysis of how to look at these things. So it's, the ice is thin, but it's holding me right now. So, I'm gonna keep looking for more evidence, so. Good question. Any other ones? Okay, thanks. Sorry, Patrick, I did it to you again.
That's fine.
Happy Thanksgiving.
We do weather.gov quick, and then I'm going to give away what I was going to talk about, because it would be cool. We can go back on Alicia Bentley's maps, look at what actually happened. That was a Viz 5D display, and it got the main features, but I think what is incredible is the actual data itself. So first, this is weather.gov. What you'll notice, here's the remnants of our snowstorm that hit us. Some places in the mountains are getting 6+ inches of snow, exactly what happened in Beaver Dam, which is right here. Pretty interesting. This is interesting in and of itself. We have freeze warnings all the way down in Alabama, frost advisories down to the Gulf Coast. This happens January, rarely, probably like once or twice a year, and this is happening in November, after we've had like record warmth for 5-6 years in a row. So to see something like this is kind of interesting, that this cold air is getting all the way down to the Gulf Coast and producing maybe frost. You wake up on the beach and it's frosty. It's November also. It's not, mid-January where you might expect this to happen and then it warms up. So that's interesting. And then here's the storm that was record-setting is going to eventually rotate around the storm that's currently sitting off the west coast and make impact to California. And you can see there's winter storm, flood advisories, wind advisories. Some of these mountains are getting 100+ inches of snow. They get 700 in a year, so this is 1/7 of their total snow in November. So pretty interesting there. Otherwise, you can notice not much going on. There's a little bit of winter weather going to impact Montana, and that's going to be set the stage for us for the next week. We'll be colder in the 30s. But if you're traveling around the Midwest specifically for Thanksgiving, it'll be perfectly clear, which is good. Earlier model runs had maybe a snowstorm for us on Thanksgiving, maybe a big ice storm in the southeast. It doesn't look like that's panning out at the moment. But if we could go to Alicia Bentley's maps, please. And I'll point out to Eleanor's question, sort of the differences between this storm and my storm that we're focusing on here. And because this includes the GFS analysis, which has exactly what happened essentially. So if we could do North Pacific here, and then we'll go to valid times. Let's see here. Let's do Monday would be good. And then if we switch, oh, that's perfect. Okay. So here's what we were looking at. Here's the little blip, the storm forming. If we scroll forward to Tuesday, you'll watch that same development. We saw this in Viz 5D. Here it is. Develops a jet stream is presumably, maybe if we step back actually a few clicks, there's a pre-existing jet stream that also interacts with right in the right entrance region. This is exactly where the storm is forming at low levels. There might be some influence in the upper levels as well. Let's step forward to 0Z Tuesday. Here's our storm. If we keep going to one click, this has dropped now. Maybe I was looking at tropical tidbits. Can we get tropical tidbits actually? Sorry, it has the low highlighted. I don't want to count.
Right. It's hard to
Because
do.
I don't trust myself to do that. But I'll show you what this storm did. If we go to models, and we'll do the same sort of thing. If we get switched to, at the bottom, regions, North Pacific, here we go. And then if we go runtime, we'll go back to, we can go Tuesday. And so what we're watching is right here, 987, low pressure system. If we step back one click, one back the other way, one more. Can you go backwards actually?
I thought it was going backwards.
Oh,
It is, but it's
It is?
but it's the wrong time. You're looking at it's November 21st.
oh yeah,
so
okay,
we gotta
that's
get
why.
there. You're not all the way back. That's all.
There we go, okay. This will be perfect. So 998, here's our storm sitting. We'll go one click forward. 982, so that's 18 millibars, or 16, sorry. One click forward. 954, This didn't actually happen, that's 28 millibars. What actually happened was 26 millibars in 6 hours, which ties the record that's ever happened. And this happened right off the coast of the western United States. What's the difference between this storm and the storm I'm studying? If we go one click forward, this storm takes us southwest to northeast track, which is typical of bomb cyclones over the northeast Pacific. My storm, as it was developing, it did the exact sort of flip. It went zonally and then stretched to the southeast and made landfall around California. So it's a little more south. You might presume that this is over the ocean, and it is over the ocean. What my storm did is, if we go back a click, just once, one more. This was the location of maximum deepening, just when the pressure is falling the most. If we go one click forward, it's about whatever longitude this is, maybe 135 or something. What my storm did is it went through its maximum deepening further east and near the coast of the United States. So that's interesting. Because you would expect, you're over the ocean, low friction, you have uninterrupted flow. Along the California coast, there's a cold current, so you might be affected with this storm by that, but my storm definitely was underneath or above that cold current, so that deters any sort of vertical motion you might expect, especially in the low levels. This storm is out of the ocean, mine was near the coast, so it's just further east in its my storm did not do this rapid deepening. It only did 49 millibars in 24 hours. This one had about 60 or 70 yeah, exactly. 60 or 70 millibars in 24 hours, so a much more intense deepening, but the mechanics look like the same. You start from a very localized, small-scale diabatic rest wave at the surface. Something comes down from Alaska to give it that oomph, and it goes crazy.
Yeah.
And 2 of these have happened now in 5 years. So, and these are record-setting storms. This was the record, if we go one click forward, please. This is the record lowest pressure for that longitude and latitude ever in the history of records. So this just happened. My storm in 2019 also set the records in California, a little more south and to the east. But 2 of these things happening right off the coast of the United States, you can imagine high impacts, and we've seen that from this storm and the storm that I'm studying as well. Not to be understated that even though it was off the coast, Western Washington, people in Oregon, who cares? They're getting slammed by high winds, rain. Some of these places, Northern California, I said 100 plus inches of snow. So it's basically like it made landfall, even though it didn't. Because you might imagine the pressure gradient, even though it's off the west coast, is still extreme. And you can see that from a high, just basically standard pressure, 1,010 to 942 in this small corridor, and you get extreme winds. And they're parallel to those bays, which is what Professor Martin was talking about. And even because of the cyclonic rotation, it curves up to match the curvature of North America, which is bad for the people living there, but good if you want to accelerate the winds in that region. So, and this was nailed by the forecast, as
Yes, it was.
we showed. You know, the lowest pressure that the GFS showed was 938 in its runs. It reached 942. That's pretty good.
Yeah.
And when originally I was showing this, I was saying, well, this might not actually happen. This is an anomalous event. We showed that. This rate of deepening might have not happened last Friday. I was saying that. It did. And so why? That's a question to be researched. Why did it actually do this? Because it seemed very anomalous and very extreme at the time, and it was, and it still is, but it actually happened. So something of interest to look at going further. And I'm sure a lot of people will be looking at this storm as well.
I would have thought a lot of people would have joined in on November 2019, but they
Right.
didn't. So hopefully the brouhaha will pass and it'll be Oz again.
That's right.
That's what I'm
exactly
hoping
right,
for.
Yeah.
Too complicated.
Yeah. Maybe not so complicated though. Maybe these are routine things. It's just the rate of deepening of these 2 storms are what's not routine.
Yeah.
I'm out of time. Are there any questions about
I'm terribly
what
sorry.
I said? No, that's really fun. It's going to be colder in the 30s and sunny and more November than we've had in the past here, I'll say. I feel like November and Thanksgiving and Christmas have been 50s and 60s, which is not normal for here. So 30s and sunny will be nice. But if we step forward, let's go to just Thanksgiving Day while we're on here. It's the 28th. You see, here was our snowstorm. We just keep stepping forward all the way to the 28th. So see, we barely get any precip here.
Yeah.
Strong northerly winds, though, that'll be the story. You can see the thicknesses are low, they're in the blue. Basically from the north, and there's a strong pressure gradient. So we might expect strong northerly winds. That'll be the only thing that really impacts travel, you see, over much of the eastern portion of the United States, and even the western portion, it looks like. So, any questions or comments? All right.
Can we switch back to my Mac for one last moment? I wanted to tell you all this. Patrick, thanks so much for that. I have, where is it? We are officially the warmest ever from September 1 to November 21st. And this is the time series that proves it. So even in the midst of all this exciting weather, the climate is still cooking. And it's cooking in a way that's never done before to this point in the late fall, early winter. So we are in uncharted territory. And maybe some of these things we're seeing are manifestations of that. I'm not going to jump on that bandwagon yet. I want to understand them first, but I think there's something interesting about their co-occurrence. So that's the time series. We are the warmest ever to November 21 in 78 years. So that's what I wanted to say. I interrupted myself and didn't do it. But Pete, thank you for driving through Viz 5D. Patrick, sorry I took your time. As always, you did an excellent job in the limited time you had. And we'll see you all after the break. Eleanor, if you got a question. What?
2019 compared to
Oh, in this?
Yeah.
I don't know off the top of my head. I don't know. And this is the whole hemisphere, not regional, so. Okay, we'll see you all. Have a good holiday. Pete, thanks again. Patrick, thank you.
No, he said that circulation was,